We're now going to turn our attention to the implementation of the bridge pattern, and this will give us a chance to talk about various aspects of implementation. So, we've seen, the bridge pattern is designed to shield client applications, basically the application code, from the details of the underlying composite structure. And so we define something called an abstraction, which is basically the interface or the API that the clients access. The clients never access the composite structure directly. They always access it via the abstraction. And the abstraction in our case is something called an expression tree. And you can see here that the expression tree is a C++ class. It's got something called a ref counter, which stores the root of the composite implementer hierarchy. And we're going to look at the implementer ref count, implementation of the ref count class here in just a minute. This is a clever class that's used to ensure that memory is managed properly by the program. So as you pass things around and they get moved back and forth by value, that the reference counting is done so that the objects automatically clean themselves up when they're no longer in use. So we'll talk more about that in a second. That ref count model, by the way, is very common in C++ because it lacks the automated garbage collection that you've come to know and love with Java. Here's the constructor, or one of the constructors of expression tree. As you can see here, it takes a pointer to a component node. This is basically the root of the composite implementer hierarchy, and it goes ahead and it stashes that away using the base member initialization section to initialize the ref counter object, which itself is encapsulating the component node hierarchy so it can manage its memory properly. And we'll talk about that in a second. Obviously, there's a bunch of methods defined in expression tree. We're just going to focus at the moment on the accept method. And the accept method is used when we start talking about the iterator and visitor patterns later. But for now, this is essentially one instance of the bridge. So when someone invokes an accept call on an expression tree instance, as you can see, what it does is it says, the accept method for expression tree says root underscore arrow accept. And as we'll see, the arrow method on the ref counter does a little bit of magic. This is what's called the delegation operation. And it'll go ahead and essentially allow the accept call on the expression tree to be forwarded to the appropriate method that's part of the underlying composite, the implementer hierarchy, as the bridge likes to call it. So that's the bridge part. We're forwarding that call. And that will then, of course, actually do the real dispatching. And when we get to the visitor pattern, which will probably be tomorrow, you'll see how that works under the hood. It's very cool. You can do various things with this expression tree class. For example, here you can see that we can actually subclass expression tree. So we can make ourselves an instrumented expression tree. And the instrumented expression tree is going to log the start and end of each of the calls. So it's just an example of how you could surround the actual logic with some logging and do that transparently to the client. So we could transparently encapsulate the underlying expression tree with something that logs every call to it. You could also do something similar. You could have a synchronized expression tree, and the synchronized expression tree also inherits from expression tree, and it goes ahead and uses the scoped locking idiom, or what's also known as resource acquisition is initialization in C++, to automatically acquire a lock and then make sure that that lock is held for the duration of the call to accept. And then when that's done, it'll go ahead, of course, and unlock the lock. So just another simple illustration of how you can transparently encapsulate the underlying logic and do something around it. In this case, we acquire or release a lock. In this case up here, we log the beginning and end of the call. So this is kind of a diagram showing what it looks like. You can see here that we have the expression tree, which is the interface that clients use. That can be subclassed so that we can change services without affecting the client. You could also change the service without affecting the implementer hierarchy. Likewise, you could come in and plug in different implementations and not affect the clients or not affect the services. The reason for doing this is we want to be able to completely shield applications from the details of how things are used. So here you can see we're creating a composite add node implementation and using that to squirrel away inside the expression trees constructor. We could trivially replace this with a different implementation using, say, tree node as opposed to the component node hierarchy, and that could be hidden inside the expression tree. And of course, the way to do this is to apply a creational pattern like factory method or interpreter or builder and so on. But irrespective of how we create this composite hierarchy, we can then write code that looks like this. And as you can see, this code doesn't reveal anything about how the underlying implementation works. All it's doing is it's getting an object that's the iterator, that's the beginning of the iteration in whatever order we want to iterate through. We keep iterating till we're at the end. And every time along the way, we're going to do something with each of the nodes. And we don't have to know, we don't have to care whether it's implemented using the a component node model or the tree node model or whatnot. It doesn't matter. We're abstracting those implementation details away. It's also worth noting that the factor method and composite iterator strategy and visitor patterns are also relevant in this example. We're not focusing on them at the moment, but we will as we get a little bit further along. So this code is actually the implementation of the expression tree itself. I'm not going to walk through all of it, but I do want to kind of highlight a few things for you. You can see here that we have the normal complement of methods you would expect to have in a C++ class. We've got the constructors, and there's a destructor, there's the assignment operator. I haven't gone and done all the move optimizations here, but that would be an easy thing to add. Here are the methods that we define that are going to be doing the forwarding to the underlying composite, which is the implementer hierarchy that's passed in here in this particular constructor. You can see we have all the methods that do the various factories for iterators. We have ones for non-const iterators. We have ones for const iterators. Here's the except method. We're going to look more at that in just a second. And no surprise, all these methods look pretty much the same. We'll see that in a second. And what they all do, for the most part, is they forward to the root data member. And root is an instance of a ref counter that's parameterized by component node. We're going to go look at ref counter in a second, but here just real quickly is what the expression trees look like. There's a cool little factory that we're going to come and look at and talk about later. Right now, though, I want to focus on just the various methods here. You can see we do our usual trick with assignment operator, and you can also see that we have all these methods here like item and left and right and so on. All these methods are basically forwarding to the corresponding method, which in this case happens to have the same name. We could always use the adapter pattern if they don't have the same name to make them look the same from the API's point of view. And they're forwarding through this thing called root. And I told you before, root was a ref counter. So let's go take a look at ref counter. Ref counter is an interesting little class. And what it's doing is it's basically taking, it's parameterized by, or let's see, ref count is parameterized by type T, which in our case is component node. If you go back over here and look at expression tree, you can see that ref counter is parameterized by component node. And what it's going to do is it's going to reference count the accesses to the component node. And let's take a quick look at this. This is a very useful pattern to apply in C++. So you can see we've got our constructor and destructor and assignment operator and so on. And then we've got various operations here that allow us to treat this as though it's a pointer. So we can do things like dereference it, and we can use the delegation operator to get access to the underlying component node. There's some methods for getting the underlying pointer and so on. And then internally, we have these methods called increment and decrement. And then there's a little helper struct called shim. And shim is actually going to hold the instance that we're dealing with. And so what we're dealing with here is we're reference counting shim. And we have a reference count that's kept track of. And that's going to dictate when things are going to be shut down or not. So let's go ahead and take a look at the ref counter implementation. You can see that in this case, like in this constructor, when we pass in a pointer to the underlying composite element, we create a new shim that's going to hold that pointer. And then, depending on various things, we might or might not increase the count. But what happens here is every time you make a copy of this, what it does under the hood is it calls the increment method. And whenever the destructor is called, it goes ahead and calls the decrement method. And as we'll see when we look at increment and decrement, what they do is the increment method will go ahead and increment the reference count of the shim by 1, and the decrement method will go ahead and decrement the ref count of the shim object by 1. And if the ref count drops to less than or equal to 0, really equal to 0, we go ahead and delete the pointer. So this is a way of being able to automatically control the life cycle of objects based on passing them around by value. Now, of course, what you're doing is you're passing the ref counter around by value, but under the hood, the ref counter is pointing to this shim object, and it's using that in order to determine the life cycle or the lifetime of the object that it owns underneath the hood. So this is a very useful technique, and you can see that when we delete it, it deletes the underlying object. When you delete shim, it deletes the object that it's holding. And so this is a really cool example of reference counting. And there are other ways to do this. This is a way I came up with doing it. You could also use C++ shared pointers to do these kinds of things as well. And we'll talk about that when we talk about some of the implementation stuff.